So suppose you want to differentiate the natural log over here. So if your rule from the start is y is equal to ln x, now just remember that ln is just short for a logarithm with base of e. Now to differentiate this, first of all, let's establish what we do know. We know the derivative of something like, let's say, I'll just draw in green again. We know what the derivative of ln e to the x is. If you want the derivative of this, well, you know that dy dx is the same thing. So we're going to make use of this property. First of all, let's rearrange our original rule over here into something else. We're going to transpose to make x the subject. Now if we do that, x is going to equal to e to the power of y. So what we did was pretty much we transferred this logarithm over to the other side as a base of e. Okay, and if you differentiate this with respect to y, so what we're going to do here is find the derivative of x with respect to y. So this is just a reverse process. Is that we're going to differentiate e to the power of y with respect to y, and this is going to be equal to, well, e to the y, isn't it? Now let's take this a step further, so just move up here. Okay, so what we want is dy dx. So let's view this from a different point of view. E to the y is the same as saying e to the y equals 1. If we want dy dx instead of dx dy, how about we just switch the positions of these two? So in other words, we're going to take the reciprocal of both sides. So take the reciprocal. And if we do this, then our equation becomes dy dx equal to 1 on e to the power of y. Okay, so remember that if we want dy dx, it's much more pleasant to see this in terms of x instead. So we're going to make use of the fact that x is equal to e to the power of y, and substitute this right back in. And this gives us dy dx equal to 1 on x. And this is the rule that we're going to make use of for some of the following examples when we differentiate ln x. So if you were to ever differentiate this original rule over here, the derivative of ln x is simply 1 on x. Okay. So moving on to the first example here. Now if we have y equal to 2 ln 3x, then what you can do over here is, well, the 2 you can ignore for now, because you can say we've multiplied the derivative by 2. So when we begin this, so we say we have a 2 at the front, and all we're concerned with is the ln 3x. Okay, we know the derivative of ln x is 1 on x. In this case over here, we have a u value of 3x. So we're going to substitute in 3x to where x is supposed to be. So in this bracket it's supposed to be x, but we're going to make the substitution of 3x now. And if you make this substitution, remember that you need to multiply by dy dx. Sorry, not dy dx, du dx. So this is applying the chain rule. And so the derivative of your substitution, 3x, is 3. So you can see that you can cancel these two 3's out, and you're going to end up with, let's see, 2 on x instead. So as you can see, it doesn't really matter what the inside of the logarithm bracket is, as long as if it's a linear factor, because if you have 3x, 4x, or 5x, you can imagine that this number over here and this number over here are both going to cancel each other out. So just keep that in mind for some of the future problems, because you can cancel them out quite easily. But of course, if you use the chain rule every time, you can't really go wrong. You'll end up with some result like this. Okay, so over here, we have y equal to ln sine of x squared. So when we write out our derivative, now we know the derivative of the natural log is just 1 on x, but it's not x anymore in here. We have sine of x squared. So I'm going to chuck this to the bottom. And we need to take the derivative of sine of x squared. So when we take the derivative of sine x squared, what we're going to end up with is cosine x squared, because this in here stays the same, but the derivative of sine x is cosine x, but this is x squared inside. So what you need to do is take the derivative of what's in here. So we're just applying the chain rule once more. We have 2x. So you can see over here, we're just making a series of substitutions. So first of all, we recognize that the derivative of ln x is 1 on x, but this x term over here is now sine x squared. So you have sine x squared at the bottom. Take the derivative of that, because this was a substitution you made. So you have cosine x squared. Now we know the derivative of sine x is cosine x. So that means you need to account for the substitution over here, the x squared. And taking the derivative of x squared is 2x. Okay. And from here, when you want to simplify, 2x times cosine x squared sine x squared. And since these two are the same, so this over here are the same. You can what you can do is combine the cos and sine over here, since they have the same angle, and recognize that you have 2x on tan instead. Okay. Alright. So over here, quite a bit more complicated, but sometimes the first step isn't just to immediately go into the derivative function. So for instance, if you're dealing with a logarithm and there's a power inside your logarithm that's quite hard to deal with, we have x to the power of half, or square root of x over here. You can always take this power to the front. So if I rewrite out this equation over here, okay, x to the power of half. Remember that if you have a power inside your logarithm, then you can take this power, put it in front. And if you do that, all you're dealing with now is natural log of x. It's much easier to deal with than natural log of x to the power of half. We'll put this half all the way to the front and say that we can ignore that for the majority of our differentiation process. Okay. So what we want to do here really is we want to find the derivative of this section over here. Okay, so when you want to find out dy dx, we keep the half over here, it's just a coefficient, and we wanted to find the derivative of what we just highlighted in green. So 3x squared minus x natural log of x. Okay. Now from here, okay, so the half we don't have to care about at the moment, but these two parts over here, we know the derivative of ln x, we know the derivative of a combination of polynomials. So if they're multiplied by each other, then that means we can use the product rule. Okay. Alright, just to refresh on the product rule, if you have y equal to ub, then dy dx is u dash v plus u v dash. Okay, so continuing on, leave the half in front. What we're going to do is we're going to take the derivative of the first term first. So 6x minus 1 multiplied by just ln x. We're going to leave the second term alone, plus, we got to do it in the next line, plus 3x squared minus x. So in this case over here, we're just leaving this term over here, and we're going to take the derivative of ln x. Then that would be 1 on x. Okay, and just to simplify a little bit here, we have half multiplied by 6x minus 1 ln x. Not much you can do here. But for this part, we can take the 1 on x inside the bracket and divide everything by x. So that will leave us with 3x, and the negative x over here becomes just minus 1. And this will be your entire derivative term. Can't really do much more than this. I mean, you can take the 6x minus 1 inside the logarithm bracket here if you really wanted to, similar to what we did before, except just the reverse process. But this is completely optional.